Viewers, thank you for watching UBC. My name is Stephen Chunguyinka, a teacher of physics. Today we are going to discuss the topic electromagnetism. But before we look at what electromagnetism is, you could have wanted to know how some of the equipments you have come across work. For example, you could have tried to know how electric motors work, electric bells, electric drills, and so many other. You will find out that most of those items are considered under the topic of electromagnetism. So now, when we say electromagnetism, what comes to your mind? Electromagnetism is the production of a magnetic field. When electric current is flowing. So what do I mean here? That when an electric current flows in a conductor, for example, then around that conductor there is a magnetic field. That helps you to relate to the concept you did when the teacher was teaching you about magnetic fields. That was in magnetism, where he defined, or she defined, that a magnetic field is a region around a magnet or around a wire carrying current in which a magnetic force is experienced. So we are saying that electromagnetism is the production of magnetic field around a conductor carrying electric current. Simply, that is what one would say that electromagnetism is. So we are saying that when you have a conductor, for example, a wire, and that wire is carrying electric current, around this wire there is a magnetic field produced. For example, if I hold this, if we hold this, and you say that this is a wire, and that is the wire through which electric current is flowing, then you realize that around this conductor there is going to be a magnetic field due to the current that is flowing in the conductor. Now, how do we show that around a conductor carrying current there is a magnetic field? We are going to use this simple demonstration. So what a simple demonstration, we're going to get a wire PQ. This wire PQ we have it continued and connected to a battery, since the battery should be the one to produce the current. So we need the wire that you have a wire. Let me put this wire here, it's better. And then you get a cardboard. I can call it a cardboard here. The wire comes out this side. And then connect it to a battery that is a cell. And within that side have a switch. This is a cardboard. This is the battery. And we are talking about the wire PQ. So that's the arrangement. We want to demonstrate that when current flows in a conductor, our wire PQ, there is going to be an electric field produced around this wire. Okay, so we have this wire PQ passing through the cardboard. Now what happens is I get iron filings and sprinkle them on this cardboard. Then after that, I close the switch. Close the switch. Iron filings sprinkled on the cardboard, and then you close the switch. When you close the switch, the battery is going to cause the flow of current, and that current, like you remember, this is a negative terminal, while this one is a positive terminal. So the current will flow from the positive terminal when the switch is closed, or come this way, and to the negative terminal when that switch is closed. So when you've closed the switch, you sprinkle the iron filings on the cardboard, gently tap the cardboard. Gently tap the cardboard. You will observe the iron filings arranging themselves around this wire in concentric circles. In other words, that the iron filings are going to form circles around this wire because of the magnetic field that has magnetized these iron filings and makes them form circles around this wire. So that is the demonstration that when a current flows, there is going to be a magnetic field around that conductor that is carrying current. So here we are saying that a vertical wire is a vertical wire PQ is connected to a battery through a switch, and that vertical wire is made to pass through a cardboard. Then iron filings are sprinkled on the cardboard. The switch is closed, and then the cardboard is gently tapped. The cardboard is gently tapped. What is the observation? The observation is that the iron filings form concentric circles around the wire, and that shows that around this wire there is a magnetic field. Is that okay? Yes. So that is it. Now, when you look at these circles formed by the iron filings around the wire, like your teacher told you in magnetic field, a magnetic field has direction. At this point, you may not be able to tell the direction because you have used iron filings. But if you want to know the direction of the magnetic field produced, then you can use a compass needle. Instead of pouring these iron filings on the cardboard, you just get a compass needle and press it near this wire. The compass needle will show you the direction of the magnetic field around this wire. How do we demonstrate that? We're also using iron filings to demonstrate that there is a magnetic field around the wire, this time round using a compass needle. Instead of iron filings, I now remove this and put a compass needle. So we put the compass needle around this point, close the switch. The compass needle will show you the direction of the magnetic field. And what has caused the compass needle to turn direction? It is actually the magnetic field around this conductor that is carrying current. So whenever current flows in a conductor, there is always a magnetic field produced around that conductor. And this is what we are calling electromagnetism, the production of magnetic field whenever current flows in a conductor. Now, we realize that therefore magnetic field pattern, we can make conclusion from this that magnetic field pattern is drawn using circles, imaginary lines. The field lines for a magnetic field is drawn using circles, but also using the compass needle. We have said that the compass needle will show you the direction. Therefore, these circles have direction. The circles have direction. So we are saying the magnetic field has direction. We can also investigate. Since it is a field, and you know from physics, a field is a region in which a force of particular kind can be experienced. Here we are experiencing a magnetic force. Therefore, since this is a field and there is a force in the field, it means that we can investigate how strong is that force. And it is observed that actually the strength of the field produced around this wire reduces as you go far away from the wire. Meaning that the field, magnetic field, in this case, is strongest near the conductor or near the wire PQ. Yes, and then also we observe that this magnetic field, since we experience a force, and we are saying that it has direction, then this force here, or the direction of magnetic field will depend on the direction of flow of current. That direction of the magnetic field around this wire depends on the direction of flow of electric current, on direction of electric current. So briefly, that's what we can say about the magnetic field around a conductor which is carrying electric current. All right. We continue with that concept of a magnetic field around a conductor carrying current. Now, we've said that the direction of this magnetic field will also depend on the direction of electric current. And also here, we said that when you use the iron filings, you may not easily tell the direction of the magnetic field. However, when you use a compass needle, it can show you the direction of the magnetic field. Normally, the direction of the field is the direction to which the north pole of the compass needle points. When I use this compass needle here, this shows north, and then this one shows the south of the compass needle. So in this case, if you want to see the direction of the field, it means since the north end of the compass needle is pointing to the right, then it means that will be the direction of the field. But we can use a simple concept to tell the direction of the magnetic field. And there we use what is called right hand. Grip rule. Right hand grip rule. So we want to use this concept, this theory here, right hand grip rule, to tell the direction of a magnetic field around a conductor. Now students, pick whatever you can pick. It can be a ruler, short length. It can be your pen. And we are going to assume that whatever you have picked is a conductor. Hope you have picked that. I've said either a ruler or a pen or a pencil. And you imagine that that one is a conductor, and it is going to allow the flow of electric current. So we want to look at the right hand grip rule, how it helps you to tell the direction of a magnetic field. Now hold whatever you have picked, whether a pen, a pencil, or a ruler, using your right hand. Imagine that this is what you have picked, probably a ruler or a pencil. And put the direction of current. Let me say the direction is upwards, like we had initially here in our wire picture. So you grip that pen, that ruler, in your right hand, such that the thumb is pointing to the direction of electric current, the way you see me doing this. Hold that pen, that ruler in your right hand, and the thumb is pointing to the direction of flow of electric current. Then the fingers, these other fingers, 1, 2, 3, 4, are carrying or are curved in the direction of the magnetic field. I repeat, that hold the conductor in your right hand, this very one, grip it such that the thumb is pointing to the direction of flow of electric current. Then these fingers are curved, or they curve in the direction of the magnetic field. I think you get that. Okay? So let's go to our wire here. I will remove this letter to represent current, remain with the arrow, and you know that the current is now moving up. Remember what we said here, that the magnetic field pattern is drawn using circles. And those circles share the wire as the center. That's why I call them concentric. So come to this wire now. Hold it with your right hand, with the thumb pointing in the direction of flow of current. Then these fingers are curved according to the direction of magnetic field. So together, if you have drawn this wire somewhere on a piece of paper where you are there, let us try to sketch the magnetic field around this conductor. Someone, I think, has already finished. We can check our answer. The field is circles. Those circles are sharing the wire as a center. You don't need to draw very many. You can draw 3 of them and make sure that they are concentric circles. So it's better you use a compass with this wire being the center. Now the direction is according to the way the fingers have curved. So I will now come here and indicate the direction on this side and also on the other side. So that means if you do that, here the field is this way. It is actually anti-clockwise. Hope all of you have got that. Okay, so that's all about the right hand grip rule, but we need to state it so that we note it in our books. So the right hand grip rule states that if a wire carrying current is gripped with the right hand, if a wire carrying current is gripped with the right hand, so that the thumb points in the direction of electric current, then these fingers are curved, or they curve in the direction of the magnetic field. We can write it. Let's note that if a wire carrying electric current is gripped with right hand, so that the thumb is in direction of flow of current. The fingers curl in the direction of the magnetic field. So this way, without having the iron filings, without necessarily having the compass needle, as long as you have your wire, you have the battery, and the wire is connected to the battery, you will be able to tell the direction of magnetic field using the right hand grip rule. You have noted it. Make sure that the concept is now very fine with you, and you can easily use it. It's not a matter of getting it and writing it, but you should also be able to use it. Now, we are going to see other magnetic fields. Here we have talked about a wire carrying electric current. Now, I want you to listen to me carefully as we look at more ideas and we introduce this electromagnetism. Because once you have picked the introduction, the topic is very okay with you. So let's look at other concepts on this issue of drawing magnetic fields. We have already drawn one for a wire carrying current, and the current is moving upwards. Hope you still remember that. Now, suppose you have a wire. Let me say this is a wire, and it is carrying electric current, but I imagine it is fixed to the board like this. If you have a piece of paper or a book, do it this way. Because for me, I'm using the blackboard. Now for you can hold your paper or your book this way, and then you imagine this is a wire carrying a current. All right? So if you see that this is a wire carrying current, yes. Now, this current in the wire can be termed as being into the paper or out of the paper. That means if this is the wire and it is passing through this paper downwards, that the current can be taken to be out of the wire, I mean out of the paper, or into the paper. How will it be out of the paper? It means that it is now taking this direction up. The stamp will be up. When I go back to the blackboard, it means if this is a wire and the current, this wire that passes through the blackboard, and the current is coming out of the blackboard, it means it is moving outside the wire, and therefore my stamp will point like this. On your paper, if you are holding it horizontally, it will come out like this. So we are going to plot or draw a magnetic field of a wire carrying a current out of a paper. For me, I'm using the blackboard as a paper. Now, when the current is coming out of paper, it's like if I'm now here facing this wire, it's like I'm seeing the current coming to me. The same thing applies to your paper I told you to hold. When you do this, it's as if the current, you are seeing it coming to your eyes directly. Is that okay? So, how do we draw that magnetic field? When current is coming out of a paper, we have general convention or an agreement that that current on your paper, you draw it as a dot. So we are saying, the other one was the wire. Now we are saying magnetic field pattern when current, electric current, okay, is coming out of a paper. I said my blackboard is acting as a paper. You have the book which will act as a paper. So when it is coming out of the paper, it is directly to your eyes now, like this. And that is direct current coming. We are using direct current. So we represent that as a dot. And now this is your wire. Hold it in your right hand with the thumb in the direction of electric current, like this. You can now see how the fingers are curved. These fingers are now curved. And they are showing us the direction of magnetic field. So let's draw them. I said we use concentric circles around the wire, and those circles represent, first of all, the magnetic field. They shouldn't touch one another. They said they are concentric circles. And here I have drawn the circles, but I need to show the direction. When you do this, you have not shown us the magnetic field, they are just circles. There must be a direction. So using our right hand grip rule, then you realize that this is how the field will look like. Around a wire carrying current, that the current is out of the paper. And the out of the paper is represented using a dot. Now what if the current is into the paper? We go back to our book or paper. Current into the paper, you have the wire, and now the direction is into the paper, like this. So the finger is pointing downwards. This first one, the finger was pointing up. Now this is downwards. Are we following? I can now even say that, sketch that current. So we are going to say magnetic field pattern of current, electric current coming out of a paper. So hold the pen, the pencil, like this. This is not coming out. The magnetic field of current into a paper. So hold the pen to represent the wire or the conductor, and then the stamp points into the paper like this. Then this is how the fingers are curved. That will be the direction of magnetic field. So if I come to my blackboard here, this is the wire, current is into the paper, my thumb points like this, then these fingers are curved in the direction of magnetic field. And how do we represent so that it's different from the current getting out? We use a small cross. That means the current is into the paper. Now we do that. We now want our field line, the magnetic field. The magnetic field. Okay, so we now want the direction, the right hand grip rule. So here, someone has sketched that. I think you have already finished. This is how it will look like. The opposite of this one here. A cross represents current into the paper. A dot represents current out of a paper. Is that okay? So far we have drawn three magnetic fields. The other one was the wire current upwards in the wire. Now this one current into coming out. Then this is current into the paper. We have other observations. I want to draw another field pattern here. Pay attention so that you get these concepts very well. I know you can get them properly as long as you listen attentively. Now, I want to have a magnetic field of two parallel wires. Magnetic field for two parallel wires carrying electric current in the same direction. Okay? In the same direction. In the same direction. Now, let me use this blackboard, or you use the book. So you imagine these are the two wires. They are parallel. If I'm to draw them on a blackboard, this is how they will be. But to bring out the picture clearly, these are the two wires parallel. So the current is in the same direction according to this subheading. Okay? So if it's in the same direction, it means in both of them, the current is coming out of the blackboard. Or the current is into the blackboard. Are we together? That these are the wires. Okay? The wires are parallel, carrying current in the same direction. The same direction, there are two options. Either into the blackboard or out of the blackboard. So let me take a case when the current is in the same direction and out of the blackboard. So if it is out of the blackboard or out of the paper, each of those wires will be represented as a small dot, parallel. Those are the wires now. This is one wire, this is another wire. Having put a dot, it means that the current is coming out of the paper. So it is just a repetition of this one here, only that we add something small. So that is around the first wire, and then this is around the second wire. Out of the paper, hold the wire. Right hand grip rule with the finger outside, pointing out of the blackboard, out of the paper. So this is how the fields are near the wires. Okay? And when you come to that side, the same thing. You have that. because the current is out of the paper. Now, when you look at this side, the extreme end here and the extreme end here, the arrows showing the direction of magnetic field are actually in agreement. They're in the same direction. It is only here that the arrows are opposing, meaning that at this point here, the fields are opposing. The fields are opposing. But here, the fields are in the same direction. So you can even have a line like this, a magnetic field line like that. Remember, I said they shouldn't cross. So you can have it this way, then it goes like that. You do this. Now, remember I said that at this point, that these fields are opposing. And in the case of magnetism, if we have opposing, it means there is repulsion, like poles. You remember that law? So at this point, you put something like this. I can put some letter like X. And that X is representing what we call neutral point. That one is called neutral point. X is the neutral point. Suppose I ask you to define a neutral point. Remember, we have said that here these fields repel. They oppose. So at this point, this X is called a neutral point. Like we saw when we were dealing with magnets, we saw a neutral point, and we are coming back to a neutral point, but the result of electric current. Now, another observation here is that because at this point the fields are repairing, then more fields will concentrate this side and that side. And so those wires tend to attract. So we are going to say that the conductors tend to attract. Why? We've said at the center, the fields repel, they are opposing. But this side, they are in agreement. So this side, there are more field lines, and also here there are more field lines, and the wires tend to attract. Definition of a neutral point. Some people have forgotten it. We can still remember it. That it is a point in a magnetic field. We can remember it. Neutral point is a point in magnetic field where the resultant magnetic flux density is 0. Sometimes instead of using the magnetic flux density, you can as well say where the resultant magnetic field is 0. Sorry. So you can as well say a neutral point is a point in a magnetic field where the resultant magnetic field or resultant magnetic flux density is equals to 0. Is that okay? Now, I want to give you this work also. Can you sketch for me parallel wires carrying current in the same direction? In the same direction, but this time the current is into the blackboard or into the paper. Yes? Try that very fast. magnetic field pattern for two parallel wires carrying current. This time when I say current, you just know that I'm talking about electric current. Carrying current in the same direction. But this time I want you to sketch for me the field when the current is into the blackboard. When the current is into the blackboard, this time here the current is coming out of the blackboard or out of the paper. Someone has already finished? Yes? Someone has finished already? Right. You can now check your answer against this one. Current into, we said it is a cross. Good. A cross into the paper. Now this is the what we are saying here. Into the paper. Now the thumb should point in the direction like this. The thumb is here into the blackboard, into the paper, even here into the paper. So how does the field look like? Someone has already finished sketching it. It's now very simple for everyone. Okay? I don't want to use very many. I want the diagram to look clear. Right? Into the paper. Here we are. So that will be clockwise. Clockwise. Draw that in thing. Now you observe again that at the extreme ends of the wires, the fields are in agreement. So it means we can continue this line like that, and also like this. Okay? And then do this, and here do that. We said that at the center, since the directions are opposing, there is repulsion, so there are very few field lines at the center and more field lines at the extreme end. And then we say that this X is a neutral point. That's what we said, is a neutral point. And also the wires tend to attract. Okay. What if now they are parallel wires, and those parallel wires are carrying current in opposite directions? That means I have two parallel wires. I have two parallel wires, and those two parallel wires are carrying current in opposite directions. That means that one can have the current into the blackboard, then the other one has the current out of the blackboard. You get the point? Yes. And you can easily sketch that very fast so that you will check against my answer. Sketch a magnetic field pattern around two parallel wires carrying current in opposite directions. Carrying current in opposite directions. I'm waiting for the answer. Then we check it. Magnetic field pattern. Magnetic field pattern for two parallel wires, this time round carrying electric current in opposite directions. So get the two wires, meaning that one can be into the blackboard, then the other one out of the blackboard. Okay? So this is what you have done. Let me say this is one of the wires out of the board. Then this is the other wire entering the blackboard. Good. Out of the board, into the board. Out of the paper, into the paper. So you have these lines here. I'm beginning with 2. Don't want very many because I don't want to disorganize the diagram. Now you realize this is out of the paper, out of the blackboard, the thumb. So you have this, yes. Then here into the blackboard, wow, the finger, like that. Now, this time round, you realize that at the extreme ends, the fields are opposing, but here they are in the same direction. So you will have this, you have that, you have this, and something like that. All right? So that will be the field pattern for two parallel wires which are carrying electric current in both directions. Okay? Now, I want to give you this exercise here, just something small. Says I want you to try this, just right. Just 2 sketches only. Sketch the field pattern around this wire carrying current. Sketch the field pattern in this diagram below. You know the symbols that these ones here represent. Thank you very much for listening to me. My name is Stephen Chungwinga, a teacher of physics. And if you want to consult further, you can get me on this telephone number, MTN 0772 836129. For our students there, please stay safe. Stay safe. Avoid being in those congested places, stay safe. We meet again. Thank you.